Picture here. Excellent. This is, if you know your JWST iconography, this was the very first picture released. This was not planned for release. This is showing that the telescope was focused and aligned on axis. This particular star was picked because everybody was sure that it was all by itself. And if you carefully count, you will see it's being photobombed by about 200 galaxies that were previously unknown to science. So this unplanned photograph speaks to me about optimism. This, of course, was released before the telescope was focused across all the field and everything had been activated. But it was such a beautiful, wonderful picture that the powers that be released it to the public to show the progress. And this actually sits on my wall in my office to remind me to be a little optimistic. So today's talk, I'm going to talk about space observatories. You will see quite a bit of JWST, but you will see some other friends out of my personal history, largely the Chandra X-ray Observatory, my first assignment. And we're going to talk about lessons from the development of these two great observatories and what can it tell us about the future and the development of other future large observatories. So I did want to start with the formal presentation with this picture. This picture is actually the most distant, earliest black hole observed in the universe, and the two missions that I got to play a part on contributed to this. So as an engineer building a product for a set of customers, scientists, it's these types of performance pictures that brings me great personal pride and satisfaction. So in terms of the origin story, and hopefully why you should be listening to me about building space observatories, I'll start way back in the beginning. I'm a space age kid. My father was an engineer in what I call the first space age, and in fact worked on the Vanguard launcher when he worked at Martin in Baltimore and met the woman that became my mother. I was born in early 1961, and about almost exactly 5 months later, Alan Shepard became the first American in space. When I was about 5, visited Disneyland with my brother, my uncle, my grandparents. My uncle took that picture. This is a fun fact. You know all 3 people in that picture. You know the tall man in the middle, I hope. And I will leave it up to the creative or the board to figure out who my brother is, but maybe you'll ask, or you'll figure it out by the end here. But it was about this time that I found out, because I wore glasses, I couldn't be an astronaut. Decided to be a scientist with a little bit of wavering hither and there, subject this, subject that. I've pretty much hewed to that path over the last few decades. So very quickly put, here is a pictorial resume. I've worked a number of technologies, but largely here is the Chandra X-ray Observatory, the 2 ground tests, worked on our version of TPFC, ConX, LISA, helped develop the Starshade, many years on JWST, took part in all 4 of the decadal mission studies. I think I'm the only one that was on all 4 teams. Worked on some unique configurations for large future observatories based on an inflatable primary. So that's kind of pushing the aerial density to the limit. We actually proposed a 14-meter far infrared terahertz observatory to the last probe call. Unfortunately, we were not selected. So I want to remind you that astronomy is an observational science, and my pithy quote there is being covered.
So, okay.
That helped a little. I think I need that corner less than anything else. And this quote from Ricardo, who not only was the principal scientist behind Chandra, but was then the Space Telescope Science Institute manager, reminds us all that astronomy and its various guises are all observational. That is, the science is rooted in the ability to make observations. And for the last 400 years, this has meant telescopes. When you design new systems that make that on the right here is the same supernova remnant, Cas A, taken with the Einstein Observatory built in the 1970s, actually on the grounds of Space Park where I work. And this was the same image of the same object taken about 20 years later with Chandra. The neutron star is clearly resolvable. The colors relate to the individual elements in the supernova remnant. And for those astrobiologists in the crowd, along with the detection of hydrogen using visible spectroscopy, all of the elements needed to make DNA are present in the supernova remnant. So when we talk about the search and the path to life, making those elements is step one. Okay. That was such a good slide. We are stuck. Okay. I want you to know, especially for all the engineers in the audience, we did test the video. Okay, let's stop the sharing. See, now it's working. Yeah, there's something
But you
wrong.
have to go back. So you, can I?
Yeah.
Resume.
Good question.
This is probably my fault for muting you. Share again. And then you have to go through the whole rigmarole.
Okay.
Okay, now it should work.
Okay.
Sorry.
Okay, so now let's try it again. So this was a previous mission. The new mission that replaced it was a giant leap in performance. We can also take the same pictures for Webb. So here's the Eagle Nebula, the famous Hubble picture in the JWST image. Here is Spitzer, previous infrared flagship, and the same scene taken with the JWST near King. This has been the trend in science in the entire telescopic era. This fine-looking gentleman is Hans Lippershey, frequently credited as being the creator of the telescope. Here's his patent application in 1608. But slightly more famous from the early telescopic era is this gentleman, who is more famous for pointing it up, but his actual contribution was to increase the quality of the optics. He engaged fine Venetian spectacle makers. There's a great book called Galileo's Telescope, and it includes lots of his letters expressing his displeasure at delivery times and costs and quality, proving that nothing has changed in optical subcontracting in 400 years. He also did write about it, right? Starry Messenger. So he was a pioneer in many fields, but fundamentally, Galileo was a technologist. That technologist powered a leap in understanding about the universe. So in case you don't believe me, this trend has been going on for 400 years. Here's his telescope. And this is the largest telescope in the world. And it drives science, and science drives it. As we zoom in, these are the last 50 years. And you can draw some trend lines for both the ground and space, and the trend is always up. So this is element one of our story. And then we want to ask the fundamental question, why is building these new systems so hard? We've established the first element of our story, bless you. First element of our story, that to men, science, and progress in science, we need to develop new systems that are a lot better than the previous ones, because that's how you get funded. These are expensive. No one's going to fund you to do 2% better than the previous generation. It's got to be an order of magnitude or greater. So I'm not above asking for help when I need a deep question answered. Lady behind me is Minerva, Roman goddess of wisdom, amongst other things. She's famous for being born fully mature, which is why she lives on the Great Seal of the state of California. Because California entered as an independent nation, not as a territory. Fourth grade California history. But she's going to remind us that these new complex systems are not born mature. And in fact, to create them, I guess she beat Churchill, blood, toil, tears, and sweat. There's a few calculations involved. And because she is a Roman goddess, she is required by all the laws of my presentation to speak Latin. And that means through dragons to the stars. So my literary or colorful illusion when I'm at work is design problems, design challenges, or dragons that need to be slayed. So in terms of what do we mean by new complex? What does that mean? Not everything we build is a new design or is complex, but new levels of performance going into unknown or difficult environments requiring new materials that have to be understood to behave for long periods in these unusual environments, new technologies, new combinations. So for example, one of the key features of Webb's design is the telescope itself is larger than the rocket. So it folds up, but it's got to be cold. So we have a parasol approximately the size of this room that radiatively separates the telescope from the sun, allowing it to radiate its heat. That was entirely new. All of that had to be figured out. A new mission, and sometimes it's just a new customer. Complex, significant constraints. I think everybody here has done enough either physics or math problems. You can write out one simple little equation, but all of a sudden you start having variables in both equations and systems get more and more and more complicated. So significant interactions or interfaces, but other constraints, cost, funding, time, mass, volume, risk, ... JWST checks them all. It's the very epitome, it's the poster child of new, complex, important. I didn't put on visible, politically, I didn't put all that stuff on. That's on there too. But that's more a job for the managers than the engineers. So let's talk very quickly about the process of design. So we've established that to power science, we have to do something new. to justify the funding and the attention. It has to be significantly better. And that comes with the burden of newness. So very quickly, as you begin to design or imagine a new system, you want to think of all of the possible ways of achieving your goal. You want to think through the problem and determine as many ways you can solve it. This, in fact, is where imagination lives. This is one of the key interactions between scientists and engineers in development. Literally standing in front of a whiteboard, changing the configuration of the observatory or the instrument or whatever you're trying to build while maintaining the science, but perhaps simplifying the design, getting rid of complexities and trying to get as many things off my new and complex list as you possibly can. Want to study the various options in preparation of selection. I'll say it and I'll keep saying it. This is a new design. Not sure how it works. So making a definitive decision on how a design should proceed without complete knowledge is always a dangerous thing. So leaving your options open, leaving rooms to retreat, move forward, move backwards. It's a very dynamic time, and working together, leveraging everybody's understanding, scientists and engineers holding hands, all that metaphor is very important for a successful mission. You want to avoid a failure of imagination. This means either ignoring an opportunity or ignoring a problem that nobody thought was a problem because they didn't want to raise it. Want to get the architecture right. You do not want to fight the physics of your device. You've heard the old joke about teaching a pig to sing. All you're going to do is not get the pig to sing and annoy the pig, right? You can't fight physics. All you're going to do is bash your head against the wall, spend time and money. So understand the physics. Quite actually, a few of my patents are understanding the system and turning a vice into a virtue. So one of the key aspects of the design process is understanding how the design works, because it teaches you how it fails. The purpose of detailed design is the mitigation of those failures. It also helps you recognize or design in the system's one big fundamental problem. Every new system or every complex system has one. If you have more than one, you are not guaranteed success. Why did I just say such a bold thing? Because I can always optimize one variable over a design. In general, if I don't know how the system works, I can't be guaranteed that I can optimize two with the same design point without fundamental compromise. So getting the architecture right is really channeling and focusing on the one big fundamental problem. I'm going to say this, and a couple of these slides are actually going to show up in the end when we talk about how work is beginning to happen on the Habitable Worlds Observatory to show that these lessons actually live in practice. And the really ugly truth is, for a brand new system that's a big leap, that gets us the science we want, our knowledge is very immature. Put very simply, we don't know how new things work in sufficient detail, especially in the beginning. Anybody scared? I am. Should remember, failure is always an option. This is not a movie. Ed Harris can't sit in his chair and intensely, argue the telescope into compliance. It has to be a deliberate act. Have to understand the two main causes of failure in design: imperfect parts and incomplete understanding. The imperfect parts and processes are managed by process called error budgeting or tolerancing. We'll talk about that in a little bit. And incomplete design and fixing of errors. This is the evolution of the JWST design from proposal era. You can even tell, even in these fairly low resolution images, it looks different. Here's a PDR. It's fixed a number of problems still apparent. Changed to the CDR version. And then even in the final design, we had to add features to solve our radiator deficiency. What links these two aspects of design is modeling, simulation, calculation, prediction of performance, whatever you want to call it. It's all that math that Minerva was talking about. So I'm an engineer. I like to make plots. So here is an artistically drawn graph teaching you the role of modeling throughout the life cycle when we are in the pencil sketch stage here. Okay, and that's actually a real sketch from one of the early architects of JWST. And as we move in along the design manufacturing and the design process, the accuracy and the fidelity and the completeness of the model continue to increase. You can also think of this in terms of the types of questions that have to be answered. When you're in the early phases, the ideation phase, and you're looking at 15 concepts to do quick trades about this and that, you don't have the time, you don't have the money, you don't have the resources to go off and build a 10 billion degree of freedom model. Right? That's what envelopes and spreadsheets and experienced people are for, and that's why you want to have some customers, some scientists in the room, and some engineers in the room to do some horse trading. Coming out of that, you would decide which one of these versions should be built for various business and performance reasons. We want to understand the distribution of possible outcomes of our design process. And then finally, which one did we build? And is it changing throughout life? And then frequently, you'll study what's happened to the ongoing system, and that'll give you ideas for the next one. Can also be framed in adjacent or corollary questions. Does the initial concept work? Once we establish it will work, can we do it with some level of constraint? Funding, technology, whatever it happens to be, and then understanding how it works and fails in detail. This gets fixed, and then we'll prove the one that we built will work. That includes workmanship. That is, you have to design it right, but you also got to put it together right. That's another set of checks. And then asking ourselves, is it still working? So we can develop a framework. So I apologize. There's a little bit of math in here. Please do not be scared. Okay. They're essentially as visual aids. So let's get started. And this little simple diagram is essentially the design process. So we start, we'll make a model or simulation of the system. We're going to understand its sensitivity. So when I mean sensitivity, these kappas are the key performance parameters, and the W's are the system parameters. So we establish those sensitivities. We understand the uncertainties, that is our ability to machine or buy a piece as we want. This is dealing with imperfections. We can predict surface performance and its distribution, ask if we've met our requirements, or is the design complete? And if the answer is no, you come back and update the model and go around until you're done. And once you've met your requirements and you've got a complete enough understanding of the system that you're confident that the uncertainties are small enough that your probability of failure is tolerable, you exit and build the system. So we can represent the model in various stages. M here means model. This is the system parameters. This is the performance. an M here is not a scalar, it's what I was trained as a physics student to call an operator. So think of it as kind of an abstract, think of it as the model. Okay. So you put these parameters in this model and it predicts the performance. Okay. Now, what I really especially want you to watch is this subscript and this one. So we determine by some means, cost, schedule, risk, heritage, etc., a design point as represented by these mu's. For those of you that have taken statistics, yes, that is a mean of a distribution. That's the intention. That's the design point. And it predicts a nominal level of performance indicated by these kappas with the bars on it. And essentially, this blue line is representative of this design point. I did not write that same graph 15 times, so it's representative. Okay, now we also understand that nothing is perfect. So we do what's called a tolerance analysis. Okay, so the same way that you should at some point have been exposed to the propagation of tolerance, this extends to complex systems. Sometimes these partial derivatives are actual analytic functions. Sometimes they're determined by computer. Don't worry about it right now. Just think of it as the sensitivity. It's the rate of change in performance with the rate of change of one of the M sub K parameters of the system. Okay, so you add this up in this way, and this is essentially an addition of variances for those of you that have taken statistics. And it gives you an uncertainty or the width or the distribution of the system performance parameter. Okay, and then with that, if you know where the requirements are, you can calculate the probability of success. Okay, and so that width is again this nifty little formula. Watch the index. Okay, so we can plot the probability of success by looking at how many sigmas, how many widths are in the region of our requirement. And once we get a lot of them, we're sure that we're going to be successful. And then as the error or the uncertainty gets fatter, the probability of flipping outside the allowed region increases. And you will note that this is a logarithmic scale. So this is really quite a cliff. Okay, that costs a lot of money to be way over here and essentially over designed by factors of 10 or 100. So typically we spend our life right here on the edge of the cliff. Now the model gets revised, right? You find some problems, you fix it, you go back and change the design. But I will draw your attention to this nasty little secret. All the terms are here positive. So every time you increase this number, assuming that these aren't identically zero, which is not a real or a very interesting case, this number gets bigger and you get closer to the precipice and your probability of success drops. Bummer. So this goes on and on and on and on and on until finally you're convinced that the performance is acceptable. All of the relevant elements of the design are in the system, and you get to what I call the omega-th iteration. Now, it's all a nice theoretical description. So the real question is, does this actually really happen in the real world? And the answer is yes. I'm going to give you a couple of examples. When we proposed what was called AXF at the time, now called Chandra, it was originally going to be a serviceable mission with multiple generations of instruments, not unlike Hubble. Soon after we got confirmation that we were okay for the program, the phone rang, and there was a small change in the budget. Bummer. We re-architected it. understood the design, changed the architecture, and went to a non-serviceable, simpler mission. Launched in 1999, still operating 25 years later, going on 26th year of its 5-year mission. And still maintaining incredibly high availability. Webb JWST also had its design evolve significantly, although for different reasons. Here's the PDR version. You can see booms holding out the sun shield, solar arrays on the side. Here, when you get to critical design review, the edges of the sun shield are straight. This blocks out the views of the hot spreader bars, which would have ruined stray light. You don't see any treatment around the primary mirror to reduce stray light. The solar array is in the back because when we put it on the side, the spacecraft overheated. So again, as we understood through modeling and simulation how the system did not meet requirements, the design was changed to fix those problems. So this is called the doctrine of successive refinement. Okay, and here's an even more interesting plot. This is the size of the JWST thermal model. So the number of nodes, you can think of it as the number of individual variables. Over time, in this case, the model was updated 48 times. So when I said on and on and on, I wasn't kidding. Okay, and here's various points in the program. System requirements review. When we wrote the requirements documents, the first requirements documents, only 7% of the thermal model existed. Now, what's interesting is I didn't put this chart together until a year after launch. I'll be doing it now for every new mission because we would have behaved a lot differently if we knew how immature our understanding was. So the lesson of newness can be described as what I would call this knowledge defect. This is endemic. That is intrinsic to new systems. To do this, okay, let's follow the logic of the story. To do new science, it's got to be a new system. It's a new system, you don't understand how it works, so you don't know the value of this at the end of the program. So as you make predictions, you have to guess where you're going to be so you can make it safely. Now, how do we handle this? Right, if you've been paying attention to any of the speakers talking about how we're going to do habitable worlds, it's because we're going to have adequate margins or reserves. Okay, so basically as this sum goes up, as MK gets larger, we debit or decrease or consume that contingency. And that keeps us on this nice green line. So we haven't spent a lot of money over designing, but we haven't fallen down the cliff of despair, if you will. So one of the things that can happen as you manage the model, so I put them in two categories. I will call them a regular perturbation. If I say regular perturbation or perturbation theory, how many people know what I'm talking about? Physics students, maybe mathematicians, okay. Good, I'm glad I added the little feature here in a second. The second is called singular perturbation. This is a new interaction or a new part of the physics that hasn't been previously explained. Regular perturbation. So this little epsilon is traditionally called the perturbation constant. So as that perturbation constant goes from 0 to non-zero, you can solve this problem in your head, and x goes from 1 to plus or minus epsilon, depending on the sign of epsilon, changes a little bit. Okay, this typically causes the slow degradation or erosion of performance that gets consumed by margin. Now, in the case of singular perturbation, the perturbation parameters here in the nature of this problem is fundamentally different. Okay, up here, there's only one solution to this complex equation. As soon as epsilon goes from 0 to non-zero, you go from one solution to two. Right, system can bifurcate. That's not the only example, but it's the simplest one. On Chandra, we had two such episodes. We had an interaction with the environment that we didn't understand and was going to overwhelm the detector, so we had to put in a magnetic array to deflect environmental electrons and not ruin the signal to noise. And the grazing incidence mirrors were also mechanically excited by imbalance in the reaction wheels. So we had to add reaction wheel isolators to take that energy out of the system. So again, most of the interactions are this regular, just kind of degradation, decrease in performance, but occasionally you get surprised with radical shifts in behavior. So the lesson of newness is not avoidable. In fact, if you want to do something for science, you're headed straight for it. You got to do something new. You don't understand how it works, otherwise you would have built it before. And you have to be aware of it in your design. And you can't be too cocky that you know how it's going to work, because you don't. On the other hand, you can take a look at this beautiful picture of the Tarantula Nebula and feel confident that you will get there. Right? You've got to be positive, you got to be brave, you got to be willing to do it. I just showed you two examples where all of this happened, and both of them are supreme successes and examples of the art. So those are the lessons. The older observatories. The challenge of tomorrow is building the Habitable Worlds Observatory. And I picked the Lubor B to stand in for it, because number one, I think this picture's pretty. Don't really like the current pictures of habitable worlds. That's a personal and artistic matter, but it's my talk, so I get to pick what I want to show. The important point here is to achieve the science, the chronographic performance, we need a system that is 3 orders of magnitude more stable than Webb. JWST is stable to a handful of tens of nanometers. Habitable worlds has to be stable to picometers. So for those of you that don't speak that, that's a millionth of a micron. That's smaller than a hydrogen atom. And I swore I was going to memorize the size of the Bohr radius, and I got distracted last night. Do it. So what else is in play? We have to remember that we live in, yes.
Can you explain what you mean by stability in this case?
Yes. So the question was, what do I mean by stability? So the light comes into the telescope, the rays hit all the telescope, and you can describe the common phase front across that set of rays. And the deviation from the ideal behavior is called the wavefront error. Okay, once you set up the wavefront error, the coronagraph can be adjusted to turn off the host star, reveal the exo-Earth or the exoplanetary target. If the wavefront then changes, that would be instability in the wavefront. And if that average error is more than a few tens of picometers, the host star is no longer successfully extinguished, and you lose the planet in the glare. So we have to remember that we're now in the almost through the first quarter of the 21st century. And we need a design that's correct for our current contemporary attitude and technologies. So what I want to do is I want to define what I call the 3 space ages. Okay, so paleo or old space. And yes, I'm borrowing from the anthropologists and the Stone Age. Did that deliberately. So the old Stone Age, space 1.0 was essentially the period from the late 40s to 1967 and the Apollo 1 fire. And basically, to get hardware in space, people dragged whatever they had laying around. Missile this, missile that, leftover high pressure suit, strap somebody in the capsule and go for a ride and hope it worked. And again, all of these systems were new, they didn't exist. There wasn't formality for checking, people didn't know, designed satellites that spun out of control because they didn't understand basic satellite dynamics. And all of the lessons that we have learned and built on so that we have high reliability spacecraft. That entered the era of reliability, our space 2.0 or the middle space age. And this little red box is the first harbinger of the next space age. So I call it the opening of the late space age. And that was when Intelsat 901 was remotely serviced by a mission called the Mission Extension Vehicle, taking it out of the graveyard and putting it into active service in geosynchronous belt. So new space or neospace will intrinsically understand servicing, reduce launch costs. This has implications not only for the prime flight hardware, but even for doing experiments and getting out of expensive analysis to retire and increase productivity in design. That I expect to be a big player in most of your careers. New launchers, optical communication, modern manufacturing, additive manufacturing allows us to make parts that were not even conceivable under traditional machining regimes. AI, ML, both in the design and the operation of the spacecraft, designer materials, and many more. So we're going to go back and ask ourselves, what does a new complex system mean? Habitable worlds will again check every box. We're going to be asking for new levels of performance. The environment isn't quite the same as is relevant for JWST. New materials, certainly new technologies for stability, and the story goes on. The architecture and the mission, of course, are brand new. It will be constrained. It will be highly interactive. So again, I want you to recall that we need to understand all of the possible solutions. So in this case, the NASA architects are starting to study a range of options. These are called EACs, the exploratory analytic cases, and their purpose is to explore the design space. We want to understand how the design works so we understand how it fails. This is a poster I generated from some work I did on our first technology development program, and it's called Factors Affecting the Performance of an Ultra-Stable Telescope, Turning Over All the Rocks. What I did was I literally had a list of 48 things that I thought would disturb the telescope, and I did an analysis to try to get rid of as many as possible. The one I could not get rid of, that's relevant here, is micrometeoroid-induced disturbance. This is not damage. If you imagine that the observatory or the telescope is a mass and spring system with a certain intrinsic stiffness, it means that mechanical system can absorb a certain amount of energy before you've exceeded your 1 picometer criteria. So 1/2 kx squared is equal to 1/2 mv squared from the micrometeoroid. And you can find out that the entire micrometeoroid environment is well above the threshold to disturb telescope. So it means we need to give it a shield or a jacket or whatever you want to call it. But we also know that it's got to be light and large and pack and do all the other things that we understand from working on the JWST sun shield. So we did some modeling, understanding the propagation of micrometeoroids through a series of thin gossamer layers in order to design an effective shield. We've even done, or I've done some tests, counted up all the holes to try to understand fragmentation and sequential fragmentation. In particular, I'm interested in trying to pick out what is the rule as a function of the properties of the impactor and the shield of the largest particle. Because if I can cut off the largest particle, the littler ones won't penetrate. So trying to come up and use fundamental science to drive this design. When we had a visitor, a research student this last summer, Miss Megan over here, the one who muted me, by the way, we took that one step further and said, we can shield most of the telescope, most of the solid angle, but not all of it, because eventually we got to do science and look at the universe. So what's going to happen when micrometeoroid strikes the primary mirror and causes stray light because we're mapping a certain part of the sky? That's not our target. So again, set up the problem, went off, started to do some analysis. We're going to use that in a proposal for some technology money. So again, understand how the system works so we can figure out how it fails. In this case, we're figuring out how it fails so we can design around it so that it can enable the science performance. This is a member of my staff at home. As you can see, he's helping me with a presentation. And this is my reminder that these types of endeavors are not only intensely detailed and important scientific and technical projects, but they're also deeply human. Okay, and Eric Smith was the JWST headquarters scientist, and I was at a kickoff for the astrophysics probe just last week. And one of his key lessons learned is it's not rocket science, it's social science. So again, that includes working with colleagues within your particular discipline and across discipline lines, because that's how we solve these problems. And just as a bit of proof, here is a series of Habitable Worlds meetings. I think there's me. I don't know if Vicky's in this particular set of pictures, but I think you're getting the idea, right? JWST was the result of approximately 100 million people hours worth of effort. That isn't one lone genius in a room figuring it out. That's thousands of people for 2 decades plus, not even counting lower tier suppliers. So to perform these systems is not only an intense technical act, or what I like to call an act of collective genius, it's also an act of collective will and focus and determination. And that is equally important to the technical. So I want to return to where we started with this hopeful view of the development of JWST. And maybe you'll take this as your bellwether so that as you think of your own careers and thinking about contributions to the systems of the future, you too will embrace my optimism that once we fight the dragons, we can get to the stars. And I'll leave you with the lovely picture of the Tarantula Nebula. And thank you for your kind attention.
Thank you so much, John, for that fascinating talk. We do have time for some questions, so if there are any, please go ahead and raise your hand.
Can you spill the beans? What's the one big flaw in JWST that you had to optimize for?
So
Can you repeat the question for anybody online, by the way?
okay, so the question was, what was the challenge on JWST? The one, there were more than one. But I think one of the hardest was an early architectural decision to keep the relatively warm, or actually the very warm, the room temperature instrument electronics close to the detectors, because traditional system solution says you keep those delicate analog signals before you convert them to digital. The amplifiers is close. Well, it put a hot box a meter away from the optics. So we had to build very carefully a thermal isolation system. And because of where it was and conduction, which is the main dominant thermal parasitic, it made getting the radiator margins right a challenge. And then, of course, we had the interaction that wasn't completely as well understood as it should have been, is originally the number of the instrument radiators were on the side of the science instrument module where they had a view to the sun shield. And so that coupled them. And so every time we were updating the sun shield, the radiator margins would go crazy. And I credit the manager at the time, which was me, that said, we got, we're at CDR, we got to kill this problem or it's going to kill us. And so we went on a search for everything that was going to hurt our thermal performance and found that we needed to do something dramatic. And that's where the deployable radiator came from. This one.
You showed this great curve of evaluation over time. You said that this was only made after launch, but now in reflection, you'll make it for every mission.
Mm-hmm.
What was that inflection point now, looking back halfway through?
So the question was, we were looking at the picture that I'm pulling up. Here we go.
Yeah.
So what this was, is this was the size of the complexity of the thermal model over time. And had we known early in the mission that the model itself was 10 or 20% complete, number one, when I went to all the change review boards and my fellow managers were complaining that systems engineering was changing their requirements, I would have responded far more pithily that we're completing them. I didn't know that. So one of the lessons for the next mission, have the world's other things, is to estimate the density that is needed to solve the thermal problem and have that as a figure of merit, so we can understand how complete we are as we approach that, so we don't overestimate our knowledge of the system. So I think that the hubris is thinking that we understand the system better than we do at the early stages. And so that leads to trade-offs that later get revealed to not be in the best interest of the program. It was the best decision at the time, right? Which is why when I gave this talk to a number of managers, I said, managers need special training because development programs are different than incremental improvements. So if you're making next year's Toyota Corolla, looks a lot like this one, and you're making a slight incremental change. When you're making a fundamentally different product that's all brand new, you need to understand this development dynamic.
So you factor people in as well, and so it's the people story as much as the technology story. You factor them in as well as a distribution. You need to sort of
Yeah.
marginalize it.
So you need to have people that have tolerance and understanding of this problem, right? There is a traditional perception that once you write a requirement, it's perfect in conception. And quite frankly, when I'm teaching my systems class, I remind everybody that requirements are fundamentally imperfect. Right, so it's that difference in philosophy can make, when a program manager is deciding, yes, we're going to do this change, no, we're not, that can make all the difference in the world. So I think it's awareness. Right? And quite frankly, most manager sets don't come from this background of developmental applied physics. And so, I'm kind of on the stump in various places trying to propagate that this is the way you need to view developmental programs in order to minimize. You won't ever remove risk. No one's got a perfect crystal ball, but we can avoid avoidable errors. Yes, sir.
That was very interesting. Thank you so much for sharing your perspective on the development mission. I was curious for the HWO. You talked about the error on the wavefront as being like one of the major challenges for the development. Is that the main one, or are there like other ones that you can foresee are going to be also?
Okay, so the question was, is the stability and the quality, the temporal quality of the wavefront, essentially HWO's big fundamental challenge? Yes, it is. All the other ones are subordinate or linked to it. So thermal stability, mechanical stability, isolation, et cetera. So yes, in that case, it's been very focused, and that's allowed for some very impressive, even early development. And I think there's a reference or two in there that will guide you to that literature. Yes, sir.
We're talking the history of the, like all the lessons learned from the yesterday. I think I like the quote from the cat, that it is social science. I think looking back at the lessons learned from yesterday and today, we can see that, the third space age is benefiting from like geopolitical tensions. Specifically, like Northrop Grumman is currently profiting from the Israel-Palestine genocide, where that they're selling military components to the Israel Defense Forces. So I was thinking, like, how can we, as a community, the astronomy community, the astrobiology community, reconcile with the military violence that's going on with our goals for human positive progress?
Let's see. I think that's a little outside of my current scope. So I don't have a good answer for you. I mean, fundamentally, I don't know how to answer you. I just don't. Yes, sir.
You showed that nice tarantula, nebula.
Mhm.
How much post-processing is there? Like, I don't know, like, what the telescope.
Oh,
takes.
quite a bit. So in fact, there is a really good YouTube movie or short documentary, because of course, the way the telescope works is it takes a series of black and white images through narrow filters. And each one of those filters are in the infrared where your eye has no sensitivity. So they're assigned colors to highlight various features. The same thing was in the Cassiopeia A image, where the sulfur or the carbon or the iron or the phosphorus line was given a different color. So there's a whole psychology. It's quite a science, and the people that do that are not only artistic, but they're also scientists. So I would just recommend creating images from web or something like that. And it's a recent video from the Space Telescope Science Institute, and it's fascinating. And those are the folks that make that picture.
So like, if we went all the way out there and we look outside of a spaceship, what would we see if we stared at this nebula?
My guess is it would be a lot more white and gray. So it'd be kind of like when you're in an airplane looking at a cloud. I think looking outside, they have colored it for, various reasons of species or turbulence. I don't know. I didn't read the 3 pages of how this image was created. But if you go on this institute's website, they will frequently discuss how they created the image and what the colors mean. Cool. And in fact, there's now kind of a rigor that, if you see something with pale, cool blues, it's radio, and gammas is orange, and X-rays are other colors, because a lot of these are now composite images, like I showed with the black hole. And that shows the real power of kind of synergistic observations. Yes, sir.
Kind of building off that, so those colors are kind of relatively arbitrary then, or are they just?
They are not arbitrary. They are artificial. But there is a rhyme and reason to them. I just, quite frankly, don't know what it is. But I would send you to that website to understand, and I remember that it's explained pretty well, even though I don't remember it. Yes, sir.
Yeah, so you talked about, you listed a bunch of different new technologies that are changing this failure is not an option paradigm. Launch costs going down, increased serviceability, machine learning. I'm just curious, like, what would be, in your opinion, how do we as scientists need to change the way we think about missions and space exploration? Like, what are going to be the biggest changes we see?
So if I could give a single shout out to the whole science community, could you repeat the question?
question.
Okay, so the question, thank you, sorry, I keep forgetting.
No.
I've got to speak to the audience in radio land. The question dealt with some of the technologies and the opportunities that are enabled by the new space age. How would I urge the science community to think of them? So number one, I think creativity is important, but especially in the early days when scientists or mission conceivers, the scientist community is talking to engineers, tell your engineers what you want to do, not how you want to do it. Frequently, I will get a phone call from somebody who has a mission idea. Oh, here, I want to do this. Right? And it's all conceived. I usually say, well, what about this problem or that problem? And, you should leave something for me to do. But at the same time, I think being conscious of these opportunities, because they're new to all of us. I don't think anybody has any particular claim to knowing everything about new space, and so I think it opens up. It gives the system conceiver, it gives the system designer many more tools to combine to come up with a successful program. So I think be creative. Always think, what is the goal of the science mission, not how is it done? But then be ready to when you get presented with a how and make sure it does the what. I hope that answered you. Yes, sir.
Sorry. A lot of stuff you talked about, the design process was very interesting, and I think a lot of lessons can be taken, even in like the context of, undergrad programs and student groups. And so, what would your advice be for different student groups on campus to help improve their design process? Considering, undergrad, the constraints that may come with, working on, sets or on SARP or on a undergrad.
Sure. So, there's a big trend on campuses, not just here.
I'm gonna ask you to repeat the question again.
You should just get a stick and hit me. So the question was, how can we take some of the lessons learned about the design process here and flow them into student and club projects and capstones and all the things that students are involved in. To make it as easy as I can, outside of saying, invite me back and let me give you the whole design lecture. I think the simplest answer is always think of why are you doing something in the design? Don't guess, calculate, know it. Design, there's makers, just go in there and kludge it up, and sometimes it works great, but you have to understand why it's working. That is part of the design process. On JWST, we had a famous incident where we put the third scale sun shield into a chamber, put a solar simulator on one side, put deep space simulators to suck the heat out on the end, and we measured the heat throughout the sun shield, and lo and behold, it worked better than predicted. And as the people in my office, they were high-fiving, and I'm going, oh my God, this is terrible. They all looked at me and said, why? And I said, because we can't explain the sign of that number. And if we have to eat it, our design we're in trouble. So rather than eat it, we formed a tiger team that I got to lead, and we dug into the modeling and the calculations, and we found missing physics. Once we put that missing physics, guess what? We explained it to a couple of percent, which was better than we needed to. Then I high-fived it, right? Then we knew it was behaving better, that we had been overly conservative, and that was why. So if I had to give just, a 30-second answer, especially early in your career, think of it as a determinative process, have a reason for doing things, be able to explain it, back it up quantitatively. And that will bootstrap you. And then if somebody invites me, I'll give you the whole talk. But that's the 30-second answer that took 90 seconds. Yes, sir.
So you mentioned how you're beyond some of the decade awards. I'm just curious what you see as the next, like, for this generation of engineers, this generation of scientists. what do you see as the next big challenge in terms of space observation and space infrastructure?
So I think so the question was, what's the next big challenge? I can't remember. I see that big stick over there in the corner. I think the next truly obvious next step is participate in habitable worlds. We're just doing pre-phase A technology. By the time even the freshmen in this room, should there be any, are out or maybe even out of grad school, that's about the time the major procurement contracts will get let in the 30s. So there's plenty to do on that particular mission. It's worth noting that the science directorate at NASA has upwards of 100 science missions of various sizes. So there is challenge in even the smallest missions of getting things to fit. Mass, weight, power, schedule, money, risk. So I'm working on a new little SMEX program that was described by one of its systems engineers as an utterly ordinary telescope doing extraordinary science. And so it's done that because we've done a few simple things, and it's the manner in which it's operated and the data that it's collecting make it extraordinary. But still, it's a supreme engineering challenge to get it to fit. And you do that with a correspondingly smaller team. So the challenge per person doesn't change. So I think in terms of big programs, there's habitable worlds, whatever the decadal picks in 2030 for the next flagship, which won't start then until the late 40s. And then a myriad of smaller craft.
Are there any online questions? Okay, great. Well, before we wrap up, I just want to make sure everybody knows that John will also be speaking tomorrow at Astronomy on Tap at Bickerson's Brewing in Ballard. So if you didn't get enough today and you would love to hear more about this with beer, tomorrow night in Ballard, I believe it's 7 o'clock. Is that 7 o'clock? So with that, I want to just thank John again for the great presentation, and let's all thank him as well, not just for the talk, but also for gifting us the James Webb Space Telescope. Thank you very much.